risk the snowstorm to drive up here.
That's true. Yesterday, yes.
So Phil was Caltech graduate, he was right over 27 years ago, I guess.
Yes.
And then he was a postdoc in Mount Stromlo, which is burned down. And then he went to Cornell after.
Long after I left.
He was a Cornell professor for the last 25 years. And for people who don't know, he's also the editor for the main journal in planetary science, which is called Icarus. That journal. So influential person to know. And we already have a whole hour of lunch presentation by Phil. In fact, there were so many questions asked by the cosmologists. I was really impressed. This tells you how interesting a speaker he is. Anyway, so be glad to hear what you talk about the Saturn's ring. Thanks.
Thank you, Yankin. Thanks for the invitation. I was trying to remember the last time I was here. You know, if Norm remembers, or it was who? I know Scott was still the illustrious leader at the time, but when did Scott first come here? Or when did it start? Was it late 80s? Yeah, I think it was not long after that. I think it was late 80s. But anyway, I'd be happy to know we recently published a paper this year that was based partly on an idea that germinated the last time I was here, with Scott actually discussing some Voyager data on Saturn's rings that we were interested in. So he made some good suggestions, and the ideas percolated for about 20 years or so, and then we got a new postdoc and suggested, why don't you work on this out and see if this idea works or not, and it actually did. So.
Was that before the invention of computers?
Almost. It was certainly before the invention of laptops, but I remember doing this on pieces of graph paper. So at lunchtime, for those of you here, then I was giving kind of an overview of some of the exciting Cassini results from many different instruments, many of which actually came from the imaging system, from the camera system. So this is going to be a somewhat more technical talk on the work that I'm involved in and my postdoc, Matt Hedman at Cornell. Some of you may know Matt in another guise. He was previously a CMB cosmologist and got subverted over to either the dark side or the sunlit side and is now doing planetary science. But before Cornell, he worked at the University of Chicago, and before that he did his PhD at Princeton with the CMB group. But it turns out that everybody does their processing in IDL anyway, so it doesn't really matter. Data analysis is data analysis. And since he worked on the CMB, he got very good at fitting very small squiggles in very noisy data. So we both work on an instrument known as the VIMS instrument, which is an acronym for the Visual and Infrared Mapping Spectrometer. And this is an instrument whose main function in life is to take near-infrared spectra of the surfaces of icy satellites and the rings and also the planet. And I showed one or two of those spectra at lunchtime. But a sort of a minor aspect of this instrument is that since it takes spectra by doing fairly short integrations, and it makes images by actually raster scanning a mirror across the scene. So it's really a point spectrometer whose design is to look at one pixel on the sky and simultaneously take flux measurements at 256 different infrared wavelengths from 1 to 5 microns. And its normal mode of operation, it then, by raster scanning a secondary mirror, it builds up a two-dimensional image of the scene that it's looking at, but actually there's a spectrum at each point in that image. But it works oppositely than the way an imaging spectrometer or a camera might work to do that, where you would take a picture at one wavelength and then change the filter wheel and take another picture and build it up. This instrument takes the spectrum instantaneously and then builds up an image. If you simply disable the imaging mode, it works quite well as a point spectrometer. You can just stare at one pixel and just take continuous spectra. And if this is a satellite, there's not a very interesting thing to do, to just look at one pixel and take the same spectrum over and over again. But if you're watching a star go behind Saturn's rings as the spacecraft moves around, you can measure the spectrum of starlight through the rings, and the instrument will take spectra as fast as once every 20 milliseconds. So that's fast enough to act as a photometer to do occultations, with the added advantage that you get many wavelengths at the same time. So most of the data I'm going to be showing you pertain to using the instrument in this so-called occultation mode, where we look at stars through the rings. And the imaging capability is disabled. But that being said, this is one image which I just put in as a pretty picture. This is an image of Saturn and the rings taken with the VIMS instrument, looking at the dark side of the planet. Red is 5 microns, so you're seeing thermal emission coming from the deep clouds of Saturn. Silhouetted above those in black are the colder clouds up at the tropospheric level that are blocking thermal emission. You can see a thin crescent of sunlight on the lower right corner. And then you see the rings looking rather faint, partly because the rings are made of ice, and ice is actually fairly black in most of the infrared. So only at 2 microns, which is shown in blue in this image, is there any significant light reflected from the rings. At 3 microns in green and 5 microns in red, ice is almost black, so you see essentially no reflection. The other point of this picture is that you can see the 3 main ring components, the A, B, and C rings, A on the outside, C on the inside. Since this is an image of the dark side of the rings, the sun is shining on the south side, this is an image of the north side, the B ring looks quite dark. And it's not because of an absence of material, it's because it's almost opaque. So very little sunlight comes through from the sunlit side through to the dark side. Hence the title of the talk, Saturn's enigmatic B ring. Because of its high optical depth, the B ring, although that's probably where most of the mass in Saturn's rings lives, it's the part that's least understood, because a lot of our understanding from Voyager of the rings came not just from taking pictures, but from doing occultation experiments and looking at either radio signals or light propagated through the rings. And because the B ring is so opaque, that's basically hampered or made essentially impossible, those measurements, until Cassini. So this is a more normal image of the sunlit side of the ring, so now you get a better idea of the relative amounts of material in the rings by the amount of light they reflect. And you can see the B ring is by far the brightest of the 3 ring regions. The A ring is intermediate in brightness, and then the C ring, up at the top there, is the darkest of all. And it's dark partly because the particles intrinsically have a somewhat lower albedo in the C ring, but mostly it's dark because the optical depth there is lower. There's just less material to intercept sunlight. You also see the Cassini division there, which you can see is not completely dark. There is material in there, and in fact the brightness of the Cassini division is not very different than the C ring. They have similar optical depths. So that's a view of the rings seen with an imaging instrument, with the Cassini camera in this case. This is a view of the rings seen in one of our stellar occultation experiments, and we have done about 20 of these. And I picked this one because it's one of the few that samples the whole ring system. Many of them, just because of spacecraft scheduling and other sort of constraints, we just get to see one piece of the ring in one occultation. And this one here, you can see there's actually there's just a data dropout. This is not an absolutely complete data set either. There's a gap in the data there. But what you see, this is basically a raw measurement. This is the signal from the star at a wavelength of 2.9 microns, and we chose that because this is the center of a very strong ice absorption band. So you get basically no sunlight reflected from the rings. Even though we're looking through the sunlit rings at the star, in fact the rings contribute essentially no flux. You're basically just measuring the star. And the dotted line just sort of indicates what the full brightness of the star would be. This is inside the C ring, this is outside the A ring. This is a scale of radius in thousands of kilometers from the center of Saturn. Saturn's radius is about 60,000 kilometers, so the surface of Saturn would be about here, just off the left edge of the plot. And you see the C ring here, fairly low optical depth that transmits about 80% of the light of the star. The B ring from here to here, mostly opaque, especially the middle part of it reflects essentially no light. We're basically down to the noise level in the instrument. Cassini division, as promised, actually rather similar to the C ring, transmits about 80 to 90% of the light. The A ring, which in this geometry transmits about 50% of the light from the star. And then outside, in this little gap here, is the F ring, the narrow detached ring outside the main rings. And this plot is misleading for one reason, and that it looks much noisier than the data really are. Essentially, all of the, you notice this noise is not very evenly disposed. Most of the noise is positive, especially if you look out here on where the star is outside the rings and in here. almost no negative noise spikes, lots of positive ones. That's because this is not really noise. These are cosmic ray hits on the instrument, or more correctly, they're high-energy particles from the radioisotope generators that the spacecraft uses for power, the nuclear power sources, the plutonium. So they generate high-energy gamma rays that go throughout the spacecraft, and they set off indium antimonide detectors just as effectively as photons do. So we see these spikes. What's not obvious here is that since we're measuring many wavelengths at the same time with different detectors, usually a cosmic ray only goes through one detector. So with work, you can look at neighboring detectors and decide what's a real signal in the rings that affects multiple wavelengths versus what's not. In this case, we haven't cleaned up this data, so it looks like noise, but it's really not. The main point of this plot, though, is to show how opaque the B ring is in the middle, why it's hard to study in these.
Negative spikes are big boulders in the C ring, say?
Yes, negative spikes. I'm suspicious of this one that goes to 0. I suspect this is some kind of a single point data dropout. But yes, but these are large, actually not boulders. These are actually narrow ringlets in the C ring that are more opaque.
What about the final drop-off?
That one is probably, since the one difficulty with this instrument is that we have to keep the star within the 1 pixel we're looking at. And the pointing accuracy of the spacecraft is about 1 pixel. So actually this experiment ran backwards. It started out here and then ran to the left in terms of time. And we were kind of lucky. We lined up the star, and apparently the star was not right in the center of the pixel. And then actually as the occultation proceeded over the next 10 minutes, the spacecraft drifted a little bit and the star apparently moved into the center of the pixel. So this was a good example. We have counter examples too, where the signal starts off up here and then sort of decays down and stabilizes. So we have a way of acquiring the star, but sometimes the spacecraft, for some internal mechanical reasons, the pointing drifts in the first few minutes of an observation. But experience shows an observation like this typically takes 2 or 3 hours. And if nothing happens in the first few minutes, usually the pointing stays rock steady for the rest of the time. It's a very stable spacecraft. We know a little bit about the B ring from looking at just the reflected light. And these are actually plots from paper by Estrada and Cuzzy. These are Voyager observations from the Voyager cameras, from images at different filters. And the top plot shows I over F. That's just reflectivity. It's basically the brightness of the rings divided by the brightness of the sun at the same wavelength. So it's just a brightness profile in 3 Voyager filters, green, a violet, and an ultraviolet filter, showing that there is some structure seen in the ring. And the bottom one shows color ratios. And what you see, in fact, that the color of the ring is not completely uniform, especially in this region around 100,000 kilometers. There are these regions that are somewhat redder than their surroundings, the so-called red bands. So the green to ultraviolet ratio is a bit higher than normal. And then there's a blue region here where the green to ultraviolet is a little bit lower. So we knew from Voyager that there were some fairly subtle color variations in the rings, although what they correspond to remains to be seen. But possibly some subtle compositional variation. But the B ring looks fairly uniform in reflected light. We can do similar color measurements with the VIMS instrument. So actually this is data. This actually is the optical depth profile of the B ring derived from the data we just looked at here. So if you take this signal and you write this ratio, this to the normal brightness of the star, and you call that e to the minus tau, and then you scale tau by the sine of the opening angle of the ring, which is about 50 degrees in this case, so you make a correction of about 20% or so. Then you get the top plot, which is so-called normal optical depth. And I'll say so-called because part of the point of this talk is that this is probably not the correct thing to do. But this is the normal way people calculate optical depths. And it's just through the B ring. So the C ring is off to the left, the Cassini division is out to the right, and the A ring is off the plot to the right. And you can see the optical depth varies from a little bit below 1 in the inner part of the B ring. It basically hits the saturation level, which is about 3.5 in this data, in the middle of the B ring. And then it's around 2 or 2.5 in the outer third of the B ring. And on the bottom are color plots extracted from the VIMS data. So the green curve Our instrument also takes spectra in the visible part of the spectrum as well as the infrared. So that's a green to UV ratio, basically the same as the Voyager measurement. So it shows, you can see the red bands here, where the green to UV ratio is higher, and you can see the blue band here. The black curve is actually a measure of the strength of the water ice absorption bands in the infrared part of the spectrum. So an interesting discovery here is that the ice bands correlate almost perfectly with the visual colors. And the reason that's interesting is that the visual colors are not due to ice. Ice is spectrally featureless. It's basically white in the visible part of the spectrum. So these red and blue bands have been assumed to represent some impurities within the ice, although exactly what impurities we don't know. The best guess is some kind of organic materials like tholins that are either implanted in the rings by meteorite bombardment or maybe have been there since the beginning. The black curve, though, clearly is a measure of basically the grain size of the water ice. This is the strength of the ice absorptions in the infrared spectrum. So the fact that the two are correlated says that the red stuff that's making the color in the visible is very tightly integrated with the ice. In fact, it says it has to be basically molecular inclusions within the ice grains. It's not separate stuff on the surface. It's not a salt and pepper mixture of ice grains next to grains of red stuff. The red stuff is actually inside the ice crystals at the sort of micron scale, because these are kind of 10 micron ice grains. That's of interest mostly to people who are interested in the chemical origin of the rings and what's going on. But we discovered something else sort of curious. We noticed that there were variations in the ice bands, though, as we looked across the rings that you see here, and it looked to us, to eye, as if there was some correlation between this ice band strength and the optical depths up here. So this is just a scatter plot of the strength of the 2 micron ice band on the vertical axis versus the normal optical depth in the rings on the horizontal axis for the whole B ring. This is the whole thing averaged, not average, but the whole, each cross is one sample with somewhere within the B ring. And you can see that there's really a sort of a bimodal distribution of ice bands. There's the somewhat weaker ice bands happen when the optical depth is less than about 1.5, and then you jump to these appreciably stronger ice bands when the optical depth is above about 2, and not much in between. So there's definitely a sort of a bimodal kind of distribution. We don't know what that means, but we'll see towards the end of the talk that we see some other evidence for bimodal distributions in the B ring, which I think is maybe telling us something very intriguing about the structure of the rings, although we don't yet by any means understand exactly what. So let's look in the occultation data now more closely. You might expect that when you look at the rings and you measure the optical depth, you would get very different answers if you did this in the visible or in the ultraviolet or in the infrared or at long wavelengths in the microwave region. For one thing, a light beam is usually only sensitive to particles that are appreciably larger than the wavelength of the light. Particles smaller than the wavelength will usually not be very effective absorbers, so you will tend not to see them. One of the curious things about Saturn's rings, and we knew this from Voyager, but it's been reinforced in spades, here's an optical depth profile done with the ultraviolet spectrometer instrument looking at a star, but this is in the UV. This is at a wavelength of about 150 nanometers, about 1,500 angstroms. This is one of our profiles at 2.9 microns in the infrared. This particular one didn't go into the inner B ring, it just covered the outer B ring. And here is one from the radio science experiment. This is done by sending the spacecraft radio beam through the rings at a wavelength of 3.6 centimeters. So this is 150 nanometers, 3 microns, that's 20 times longer wavelength, and then a jump to 3 centimeters. And other than the fact that the absolute scale is a bit different because of some technicalities, because the radio signal is a monochromatic signal that can separate diffracted light from directly transmitted light, they measure optical depths that are systematically about twice as high as we measure with stars in the optical or the UV. But other than that, the shapes of these profiles are almost identical. And if you divide these numbers by 2, you get something fairly close to the optical depths measured here. So what we found is that the optical depth of the rings does not vary to first order when you go from 3 centimeters to 150 nanometers. It does vary a bit. There's about if you correct for that factor of 2, the optical depths here are about 20% higher than they are down here. But that means, in simple-minded terms, that 80% of the ring cross-section is in particles bigger than about a centimeter, things that will block the microwaves. And at the most, 20% is in little tiny particles that only will block ultraviolet or infrared but won't block microwaves. So there's a very minimal population of tiny particles. These are mostly fairly big macroscopic particles in the rings. You can also see that there's several distinct regions in the B ring that have been labeled here. So the inner least opaque region we're referring to as B1. B2 is an intermediate region where the optical depth seems to jump backwards and forwards between about, well, on this plot, between about 1.5 and about 6. The B3 region, also sometimes referred to as the core of the ring, the optical depth is high, like around 5 in this experiment and about 3 in the optical, at almost all locations except for a few little narrow spots where it drops down to 2. And then there's outer region B4 that is a bit more amorphous, but where the optical depths are kind of like the average in this region, but not as high as in here. May or may not be a 5th region that's different out here. We're going to concentrate mostly on this B2 region that seems to be particularly strange in its behavior. So here's a blow-up. This is the end, the B1 region here where the optical depths are fairly low, and then the transition at about 99,000 kilometers into the B2 region, and this is the beginning of the transition into the B3, more opaque region. Same 3 occultations, ultraviolet, infrared, and microwave again. And notice a couple of things. This fairly uniform, rather opaque region happens to correspond to the these 2 red bands here in the visible. But the other thing is, notice here that the optical depth really sort of bounces backwards and forwards. It's basically a bimodal distribution. It likes to be at around this level here, or around 2 in the microwave, or about 4, or equivalently in the optical it likes to be around 1.3, or it likes to be up around 3. And it spends very little time at intermediate optical depths. It's like something is sort of wanting it to go one phase or the other. So one of the punchlines here is that maybe there's some kind of a 2-phase behavior going on here in the B ring. There's a moderately opaque and a very opaque phase, and not much that's in between. So this is what it looks like if you blow it up to closer to the full resolution of the data. So each of these panels, this is now all infrared data from the VIMS instrument, but from 3 different occultations, so 3 different stars at 3 different tilt angles or opening angles of the rings. And the black curve is from this star, Alpha Aura, which sees the rings at an angle of about 50 degrees to the horizontal. So a steeper angle than you can ever see the rings from the Earth. This one is Alpha Sco, or Scorpius in the middle. It's the rings, its line of sight to that star intersects the rings at 32 degrees. And then finally, CW Leo is the gray, the palest curve here, which is only inclined at 11 degrees to the rings. And of course, any particular star has a certain direction in space, so regardless of where the spacecraft is, whenever you see that star through the rings, you always see the light of the star penetrating the rings at that angle. And this shows this characteristic B2 region in the rings, where the optical depth jumps from the very opaque phase, where we get almost no signal through, where the optical depth is about 3, or again down here, to the lower optical depth region, where the optical depth is about 1.3, and we get about 10% transmission through the rings. And you can see how sharp the transitions are. Not everywhere. There are some places where you see gradual transitions, so not everything is perfect. But by and large, you see these rather abrupt transitions from one to the other, as if the ring really does not like to be at around about where this dashed line is, this sort of intermediate value here. And I'll see this intermediate value is at a transmission of about a bit less than 0.1. Anybody want to guess what it corresponds to? This was put on as a leading thing here by my postdoc to try to push a theory, although we don't know whether the theory is right yet. Anybody done any crystallography in the past? That's about the transmission if you took a monolayer of identical spheres and stacked them on the table and basically rammed them together as close as you could, so they would be sort of hexagonally close as packed. The transmission is a bit less than 10% through the chinks between the particles. So a flat monolayer ring, which is a hypothesis, would be at about where this dotted line is.
It's one layer, right?
One layer.
Not a stack of layers.
Yes, if you stack them up, of course, you can get more opaque because you can fill in the holes in the bottom layer with the top layer. So one possible theory here, and give away the punchline at the end, because I can't prove it, is that we'll see in a little bit, there's some evidence that the rings are very thin, not very far from a monolayer. And just possibly we're seeing some transition here where the ring goes from being maybe a monolayer to a multilayer. And these higher optical depth regions could be where you have multiple layers stacked up, where the ones on top are hiding the chinks in the one below. Because the point where they kind of avoid the optical depth that it sort of runs quickly through to get to the other side roughly corresponds to the close packed monolayer picture. So that's where I'm sort of...
Circles?
Yes, monolayer. So an idealized picture. Monolayer spheres. Just spheres. Yeah, not squares. No, sphere. Identical spheres. Easy thing to calculate. The other thing that's more quantitative that's shown on this plot, this is just directly measured transmission through the rings. And you notice that the transmission is highest for the star that's at the highest inclination angle, the one that's at 50 degrees, a little bit lower for the one at 32 degrees, and then appreciably lower for the gray curve, which is the one at 11 degrees. That's what you'd kind of expect, right? As you look more vertically through the rings, they become more transparent. But these curves are not nearly as much separated as you'd expect. If this was a classical layer of widely separated particles, then the line of sight optical depth would just go inversely with the sine of that angle, just the geometric path length through the layer. So the normal model is that the line of sight optical depth should be the normal optical depth divided by sine b. And that would result in a much bigger spread of these curves here, especially the 50-degree curve would be well above the 32-degree curve, which 32-degree curve is already suffering a factor of 2 between it's air mass 2, basically. Right. So this is air mass a little bit bigger than 1. This is 2. This is air mass 6 or something at 11 degrees, right? Sine b is about 0.1. And these curves are not nearly that far separated. So while the transmission of the ring does depend on the inclination angle, it doesn't change nearly, it doesn't increase nearly as rapidly as you'd think when you look more vertically through the rings. So this is a hint that the rings are not really behaving much like the sort of classical model, which is a very thick layer where the particles are separated by 5 or 10 times their diameter, and you can apply normal sort of atmospheric extinction kind of model, which is what sometimes people refer to as the cloud model. It's the model that optical physicists who look at transmission through clouds in the atmosphere use, where you have water droplets that are separated by many times their size. And that's the standard stuff if you look in Chandrasekhar's book on light scattering or something in atmospheres. That's the same model that's used. There's an indication here that the rings don't really behave that way. This is more of the same. This is the rest of the B2 region. And about here is where 104,000 is about when we go into the B3 region, the more opaque region. So you see the transition. Here we're still seeing jumping backwards and forwards between opaque and less opaque, even a very little region here. And that's about the last time we do that. And outside of this radius, or outside of here actually, the ring never becomes very transparent again. It just stays opaque for about 5,000 kilometers, except for these little places where the optical depth just barely makes it up to the dashed curve. It makes it down from about 3.5 to about 2, but that's as low as the optical depth ever gets.
Is the size distribution known of these particles in this ring?
No, well, we know a fair amount in the A ring, almost nothing in the B ring, because the size distribution mostly comes from looking at the microwave signal transmitted through the rings in the radio occultation experiments. And in the Voyager experiment, the B ring was completely opaque. So we now have some Cassini microwave data. So eventually we will know something about the size distribution, but it's not published yet. But in the A ring, it's a kind of a power law distribution from about 1 centimeter up to about 5 to 10 meters. And that's about an r to the minus 3 power law. So there's about 1,000 times more particles at 1 centimeter than at 10 centimeters, and 1,000 more at 10 centimeters than at 1 meter. And then above about 5 or 10 meters, it seems to roll off. There seems to be a cutoff. And below about 1 centimeter, there seems to be a cutoff. Or we would see a lot more optical depth down in the infrared and the ultraviolet that we don't see. So it looks like it's mostly 1 centimeter to 10 meters. Most of the cross-section is in.
Can you get rid of the smaller particles by radiation pressure, or are they just not produced?
They must be produced by impacts, and radiation pressure probably can't because of collisions with the other particles. So it's probably just simple reaccretion of the little ones onto the big ones. It's just stickiness. These are very low velocity accretion. Random velocities are a few millimeters per second. So the little ones, presumably they encounter a big one and they just stick back into the regolith and they're welded on again pretty quickly. So something happened in the transmission of this. So unfortunately all the white labels got converted to black. But it doesn't matter too much. This shows a set of 4 occultations we did of the same star in the first year. Actually, it was Omicron Ceti, or Myra. This shows the appearance of the rings. The rings were almost edge-on, only 3 degrees out. And each yellow trace represents the path that that star followed behind the rings. And this was just on 4 successive orbits of the spacecraft when the geometry just changed a little bit. And this turned out to be fortuitously a very nice geometry. And on this plot, the color coding on these stripes indicates the amount of starlight coming through. So this is an attempt to optically show what an occultation looks like without showing squiggly lines. Because the JPL public relations people say you cannot show squiggly lines in press releases. So blackness indicates the ring is opaque. So the B ring is basically opaque on this scale. But you notice if you compare the A ring here and here, you see a difference? It's quite a bit brighter here than it is over here. And on this occultation down here, which only goes through the A ring, you can see this whole region is much more opaque than the equivalent region over here. And even on this one, which just went a little bit into the A ring, it looks somewhat more opaque here than it does there. So there's a systematic difference where the ring is less opaque here than here, and you're looking through it at exactly the same angle. That's set by the direction to the star. It's exactly the same geometry. The only difference is a 50 or 60 degree difference in longitude around the ring. And here it is if you take one of those occultations. I think it's actually this one through here. And you plot the transmission versus radius, and you fold back the 2 halves of the curve, the ingress and the egress. So in terms of time, basically time starts here, runs into here, the star gets to its minimum radius, and then it comes back out again. But at the same radius, you can see there's a factor of 4 difference in transmission through the A ring. This is huge. We did not expect this at all, and we've done occultation experiments before, but only ever one experiment at one wavelength, so we had no reason not to believe that the numbers were independent of longitude. After all, rings should be axially symmetric, right? This is manifestly not axisymmetric, this ring, especially in the middle part. This is in the A ring, so this is the middle part of the A ring. It gets more symmetric in the outer part, but there's still a factor of 2 difference. So what's going on here?
When you showed us the 3 previous occultations, were they from the same longitude? The ones that
Yes, in hindsight, since they were made after this, we chose them to be at about the same longitude, yeah, to avoid this problem. But yeah, so I'm reversing the sense of time a little bit here. But you're right to be suspicious. So what's going on? The ring is clearly anisotropic, right? You look through it at 2 different longitudes, the same radius in the ring, same star, same instrument, same line of sight to the ring plane. You see a factor of 4 difference in transmission.
So where's the sun in that picture?
I'm not sure, but we're not seeing any sunlight here, really. This is at 3 microns, so sunlight should be irrelevant. That's a reasonable thing, but in fact, we're pretty sure there's no sunlight here. It's just that really is the brightness of the star through the rings.
The angle for the spacecraft changing?
Relative to the rings, yes. So this is a plot of transmission at 2 different radii, 129 and 133, sort of arbitrarily chosen. At this radius, we have 4 occultations in the black curve, and at 133, we have 3 occultations, so we have 6 different samples. And this is just the transmission versus the longitude in the ring plane, and it's plotted relative to the direction to the star. So it's the longitude in the ring relative to the direction if you were looking directly to the star. So relative to the point on the rings that's opposite the spacecraft, that's over in the direction to the star. And I'm looking around near the left answer where the angle is roughly 90 degrees. So 0 would be back up the top here somewhere. And 90 would be down here, and 180 would be down the front. So this is a region sort of around 90, plus or minus about 30 degrees. So here's 90. So what this says is that at 0 degrees, we would be looking, the starlight, we're looking at a rather low angle. The star is, I mentioned, at a rather low angle to the ring plane. We're only about 3.5 degrees out of the plane. So in reality, I'm like this. I'm squinting down through the rings at a very low angle. And 0 would mean I am looking parallel to the radial direction in the ring plane. The line of sight to the star is running towards or away from the planet. 90 degrees, I would be looking in the azimuthal direction. Okay? So there's a variation in transmission which is linked to the viewing direction, where it peaks at about 70 degrees. So not quite in the azimuthal direction, but near it. Ring a bell yet? It's a paper by Toumray, Alain Toumray in the APJ from 1966 or something like this that relates to this. This is a simulation done by Heikki Salo. These are the things we were talking about before, Yankin. This is a little patch. It's a simulation of a little patch about 100 meters or about 400 meters square in the B ring, actually. And each little thing in there is a simulated particle in the rings with a kind of realistic size of about a meter or so. And the radial direction is outwards to the right. I'm not sure if this will... yeah. And I'm told that if I back up, these things will never work again, but it did. This one is pretty robust. So the radial direction is out to the right, azimuthal direction is up. So what you're seeing is clumping in the rings, gravitational clumping, being ripped apart by Keplerian shear because you're well inside the Roche limit. So particles cannot stick together by virtue of their own self-gravity. Tidal shear wins. But it doesn't just produce a mess. It produces this ever-changing pattern, which is referred to as self-gravity wakes, is the term that's in vogue at the moment. But these are just evanescent structures that form in the ring, and they're continually torn apart. Any one of them only lasts of order an orbital period or less before it gets ripped apart by shear. But the sense of the Keplerian shear, with the inner part of the ring rotating faster than the outer, means these things always get dragged out into the sense of incipient trailing spiral structure. And this was talked about by Toumray back in the 60s as an attempt, as a possible way of explaining spiral structure, especially flocculent spirals, SA-type spiral galaxies, where you didn't have a grand spiral design, but you seem to have lots of small-scale bits of spiral structure within the disk. And he found that any disk that had shear in it like this would produce these kind of transient structures. But this is a simulation in the rings that shows this beautifully. So the scale of this, as I said, is about 400 meters across the box, and the wavelength is about 50 to 100 meters between these patches. But you can see they're oriented rather nicely, and it turns out they're oriented 20 degrees from the azimuthal direction. So when we see the maximum in signal, it turns out to be when we are looking right down the axis of these wakes.
Does not depend on anything?
It turns out it just depends on Kepler, basically.
Right.
It depends on the Oort A constant, the d omega dr, basically.
Right.
So in a Keplerian disk, it's 20 degrees, and it doesn't depend on anything else. In a different galaxy rotation, in a constant v versus r, it's a somewhat different angle. But that's one of the things that Toumray experimented with and found it really only depended on the gradient of the angular velocity law. So 20 degrees is the magic number for a Keplerian disk. And that basically corresponds to where we're looking along the wake. So this is a little cartoon that shows the view of the wakes seen from the spacecraft. And as we look along the wakes, we see through the spaces between them, and we see maximum transmission through the rings. And then when we look, when the wakes are turned away, more edge on, given that we're looking through the rings at a very low angle, and the wakes presumably have some physical thickness, they're not infinitely thin, you start having one wake blocking the gap between it and the next one, and the ring becomes more opaque.
So even at your short integration you can't resolve these sort of 10-meter type.
No, the resolution is about 400 meters in that data, so it's unfortunately it's getting close, but not quite enough. So here's just a geometric cartoon picture of such a thing. Here are two wakes. Here's the spacecraft looking through at the star.
You can't choose your occultation such that you happen to be sort of going along for a while at more or less the right speed with the ring, so that you actually have better resolution?
We're looking to try to do that. We haven't yet, but there is some scope. Yes, so with the right geometry, you can sometimes be lucky. So the transmission through the rings depends on B, which is this inclination angle from the line of sight to the ring plane, and on this angle theta, which is the look direction relative to looking at along the wakes. And if you look along the wakes at theta equals 0, you see maximum. So if you make these wakes elliptical, just to make something simple to calculate, with a wavelength lambda between them, a width w, and a thickness h, you can derive this analytic expression for the transmission, assuming that the wakes themselves are opaque and the gaps are just completely clear, which is roughly what the simulations, it's an exaggerated version of what the simulations show. And if you rotate the angle, you can easily show that you get a shape like this, and the half width of the peak in brightness is related to the ratio of the thickness of the wakes to the wavelength. So the taller you make the wakes, the narrower the slot is in which you can see the gap in between them. And the thinner you make the wakes, the less it makes. If the wake thickness goes to 0, if it's really completely two-dimensional, then nothing changes as you rotate around. It's because of the finite height of the wakes that you see the effect. So we can measure the thickness of the wakes as over the ratio of the thickness to the wavelength by measuring this half width here, which we can do from the data. So if we do this at a whole bunch of radii, this is what we get. This is h over lambda across the A ring, where each data point is at a different radius, using those same three occultations. And the answer is remarkably uniform. It's about 0.1. So the wakes are about 10% as high as the wavelength between them. And we can't measure the wavelength directly, but Toomre said that the theoretical wavelength you'd expect is the same as the wavelength for maximum sort of critical instability in a disk where the Q is fairly close to 1. So this is actually an axisymmetric wavelength, but it turns out it works pretty well for the wakes. So the wavelength is 4 pi squared g times the surface density in the disk divided by the angular frequency squared. And this is a few kiloparsecs in the galactic disk, but it's 50 meters in Saturn's rings. So we're using at the moment this theoretical number for the wake. And it's consistent with these numerical simulations that show sort of between 50 and 100 meters typically. So if this is right, then the ring thickness is about 5 meters. And I already said that the biggest ring particles are about 5 meters in size. So
Simulations also give you h over lambda. Simulations, do they give you h over lambda? Do they give you observations?
They do. The simulations also give thicknesses that are total thicknesses that are about 10 meters. So in general, yes, this is in agreement with the simulations. But I think this is a fairly direct, almost model-independent kind of result, except that the lambda depends on theory, but the h over lambda basically comes directly out of the observations.
So none of the images, I guess, are all much poorer resolutions, right?
Yes. Yeah, the best images are about 200 meters resolution, and they were taken with the hope that you might see the wakes. So we only have about 4 images. It was when we flew over the rings when we first went into orbit, and we got 10 times closer than we've gotten any other time. Normally the images are about 1 to 2 kilometers resolution. We have a very small set of images at 200 meters, and the rings just look smooth and featureless, unfortunately, at that scale. But you probably need to Nyquist sample this to see it. So you probably need 25 meters resolution for something to jump out of you in the images. So not with Cassini. I don't think we're ever we don't have any obvious way of getting that close to the rings. So we need a longer camera or a spacecraft that comes closer to the rings. Something that orbits in the rings, probably. So this is a simple model based on the wakes of what the transmission through the ring should be as a function of sine B, the sine of this opening angle. And the top plots show transmission. The bottom plots show if you took the transmission and converted it to normal optical depth. You wrote this as e to the minus tau over sine B, which is what people normally do. So normally you would see, and these correspond to a simple model where you fill in the space between the wakes with some material that's not completely opaque, so we call a tau gap, sort of a filling material, because we found this was necessary, and we assume that behaves like a normal thick ring. But then there's a geometric factor, which is just the width of the gaps divided by the wavelength of the wakes. So this is just geometric transmission. This is the fine stuff that's filling the gaps. So these are a set of curves for tau gap of 0.3 and different ratios of g over lambda. And this is a set of curves for g over lambda of 0.15 and various values of tau g. And you can fit this if you measure occultation. So those same three occultations I showed you at 11 degrees, 32, and 50, you can fit either in transmission or optical depth space. You can fit at the same radius, you can fit the measured transmission at these three angles. And you can basically solve for this g over lambda and for tau g. And it's simplest to look at an optical depth space. You can see that g over lambda tells you the slope of the line, and tau g here basically gives you a vertical offset in the optical depth line. So it's basically fitting a straight line to three data points to get an offset and a slope, to get these two parameters here. And for this purpose, this is a simple model because we assume we're looking right down the axis of the wakes, hence your question before. So we chose three occultations in which we were looking right about 70 degrees, right down the axis, so that we don't have to worry about the thickness of the wakes here. But this is in the B ring now. And so this is the B2 region here, and this is the boundary going into the B3 region. And we have three occultations, so the black and the green curves come from combining two different pairs of occultations to fit, and the blue comes from combining the other pairs. So we could do a fit to all three, but for consistency's sake, we just tried taking each pair of occultations and solving for these two parameters to see if we got the same answer. So the black and green curves lie almost exactly on top of one another, which suggests that this kind of works. The blue curve does not make use of the 11-degree occultation, so it's not as strongly controlled, and it gives a much bigger scatter of measurements. But the other two, combining either the 50-degree or the 30-degree one with the 11-degree, give a consistent answer. And it says that g over lambda varies up and down from about 0.2 to about 0.7, so the relative filling factor of the gaps goes from 20% to 70%. But the optical depth of stuff filling the gaps is remarkably constant. It's about 0.3. Now, I remind you that the average optical depth of the B ring is 1.5 to 3 here. So the optical depth in the gaps is much lower than the average. Most of the blocking is coming from this fact that 30 to 80% of the ring is blocked by opaque wake. So this is much noisier, but this is in the B4 region in the outer part of the rings. But again, the black and green curves are pretty consistent. And surprisingly, tau g is about the same. It's about 0.3. But now the average optical depth is higher, and that corresponds to a g over lambda that's now down around 0.1. So the gap width is only about 10%, and the other 90% is opaque wake. Whereas back here, the gap width is 20 to 70%. So the interpretation from this is that most of the variation we're seeing in the optical depth of the ring is simply variation in the fraction of space filled by the wakes versus the gaps between the wakes. And the stuff that's filling in the gaps is pretty much the same. And it's a fairly low optical depth, around 0.3. So our cartoon view of the rings, if you were to look at them edge on at very high resolution, would be like this. This is about 10 meters or so. This is the thickness of the wakes themselves. And we assume that the big part, based on the dynamical simulations, that the big particles, the 10-meter size guys, are mostly confined to the wakes. The centimeter size ones tend to float around. They're more affected by collisions and a bit less by gravity. So here's the tau gap of 0.3, the sort of optical depth when you look through the gap, you see about 0.3. And here's basically optical depth infinity when you look through a gap, a wake, and you combine these two together with different proportions for the width of the gap and the width of the wake, and that gives you most of the structure you see in the rings, most of the variation in optical depth. So that's our cartoon view of what the rings look like at the moment. Other people have come to similar views, and one conclusion from this has been that we have no idea how much mass is tucked away in these wakes. They're basically opaque. The transmission of the rings just depends on how big the gaps are. You could put almost indefinite amount of material within here. So some people are beginning to speculate that the mass density in the rings may be an order of magnitude more than we've guessed before, because what we tend to have done is taken the average optical depth and scale it from the A ring, where we know the mass density from density waves, and do that to the B ring. But in reality, there may be a lot more mass in the B ring, but it's mostly in these opaque wakes. So let me finish by coming back to this sort of bimodal question we talked about before. This is, again, a blow-up of the B2 region in the rings. And this shows, again, the same three occultations. 150 nanometers in the UV, 3 microns in the infrared, 3 centimeters in microwave. And this is just a snapshot, a blow-up, just to see. This is just a 2,000 kilometer range, 102 to 104. But just to show this alternation between opaque and less opaque. But just to be honest, I mean, there are a few places like this where the rings wants to make a liar out of me and the optical depth wants to be around 2 or so. But mostly it wants to be around either 1.3 or up around 3. And it doesn't very often like to be in between. This red dotted curve, again, with an optical depth of 2, corresponds to this hypothetical close-packed monolayer ring, which would have a transmission of just under 10%, or an normal optical depth of about 2. So, we tried various games, none of which have been completely successful yet. One of the things you can do is simply make a histogram of the transmission through the rings and decide whether they're really bimodal or not. And this gets confused by the fact that the different regions in the B ring behave rather differently. So this is a histogram of transmissions. It's basically total radial length of the ring that has different transmissions. And the B3 region, which is most opaque, the transmission is sort of less than 10% everywhere and is typically around 3%. Here is the B2 region, and here is as close as it comes to being bimodal. There's a zone here where the transmission is basically 0, there's spike, and then there's a broad region where the average transmission is about 10%. That corresponds to the optical depth of 1.5 or so. But the B1 region, there's this kind of a broad, it's more transparent. Transmissions are higher, but it's not really bimodal. Similarly, the B4 region, it's a bit more opaque, but it's not really bimodal either. And the very outer region is, again, not very bimodal. If you throw the whole B ring together, you get this rather messy-looking curve that's not too informative. But I still see a little suggestion here that there's at least 2 populations of optical depth. There's an opaque zone and there's a less opaque zone in between. If you stack them all together in color, you get a very colorful plot, but I'm not sure that it's particularly informative other than being colorful. So this is the last plot, and you can see there's no data plotted on here. It's just a model. This is just like the... it's the same as these models here. So this is the simple wake model. And now we said, well, what if the wakes themselves are not completely opaque? What if they are, in fact, something like one of these hexagonally packed monolayers? What if they're not really a thick, completely black object? Could we see that in the data? So the dotted curve here is the original model, where the wakes are completely opaque. So on optical depth versus sine B, that's just a straight line up here, where the slope of the line is determined by this ratio G over lambda, and the offset from 0 is determined by tau gap, which is 0.3 in this case. So these curves start at 0.3, and then they're straight lines. If you take a hexagonal closest packed, a sort of an idealized ring, which is the dash curve here. So this is really just a crystalline hexagonal closest packed identical spheres. Such a ring, even with a gap of lambda, a gap over lambda of 0, so a ring that's made up completely of wakes, above about sine B of about 0.8, this ring would start to become transparent. You would start to see through the little chinks between the spheres. So the normal optical depth would paradoxically sort of decrease as you went up. Now the transmission continues to go up, but it goes up more, the transmission goes up more than the dotted curve, which is the opaque wakes. And then we tried a more realistic model, which is sort of randomly close-packed wakes. So Matt, my postdoc, cooked up a sort of a statistical mechanics type approach where you still take identical spheres, but you arrange them randomly, but still that they don't interact with one another, but you don't force them to be in a hexagonal pattern. And then they have to be not so tightly packed, so they transmit more light than the ideal ones. So that leads to the black, the solid curves here. These are so-called randomly close-packed rings. So this is what the curves we would expect to do deviating from the opaque wakes if you had the wakes themselves were effectively a monolayer but not a perfectly packed one. So the hope is that as we look through the rings at higher angles, the optical depth will roll over and stay flat or start to come down again rather than continue to increase with opening angle. So we have not yet seen this in any of the observations. And so far I would say that these are where we have 3 occultations, and they really fit this straight line pretty well, actually. But later on, in the next 6 months or so, we'll get some occultations up here, almost literally looking vertically through the rings, and with higher signal to noise than the ones we've done so far. So we hope then that we may be able to test this notion up here. So let me finish by saying, why are we interested in this monolayer picture? I mean, why would this be sort of an interesting thing to test? Or at least does it relate to? And to sort of go full circle from where I started, years ago Scott Tremaine sort of abandoned working on planetary rings, where he had done some very nice work, and went off and worked on other much less interesting things like rotation of triaxial elliptical galaxies, and writing small textbooks on galactic dynamics and things like this, and doing God knows what other things he does down at Princeton. But about 10 years ago, out of the blue, he wrote this little paper on Saturn's rings. Yes, suggesting, what about stickiness between the ring particles? And what he did was go back and violated something that all of us have learned since James Clerk Maxwell wrote his prize essay. Some of the students should know the answer to this. What did Maxwell prove in 1857, I think? This is before he thought about electric and magnetic fields. There you go. It's a good question for graduate students. Yes, so he, long before Maxwell, Laplace had proved back in the 18th century, he thought about tidal forces, and he was the first to say that a ring could not be a solidly rotating broad sheet, because the tidal forces across the sheet would be much stronger than any plausible self-gravity of material within the sheet, assuming the sheet was made of some normal kind of material. So he said, despite appearances, Saturn's rings cannot be a nice big uniform disk, a frisbee rotating around Saturn. The outer part of the rings has to rotate more slowly than the inner part, or it doesn't work. And that was, of course, verified experimentally by Keeler when he measured the Doppler shift across the rings. But then a lot of people still thought, okay, it can't be a broad sheet, but it can still be a whole bunch of hula hoops, each rotating at their own rate, and they can still be solid. And Maxwell was the one who said, no, that doesn't work. If you consider a narrow, rigid hula hoop, it has various unstable modes. It'll go off, as I recall, right? It normally goes off center, I think. Yes, like Ringworld. So yes, so Ringworld doesn't really work, despite Larry Niven.
No, he controlled it.
Oh, okay, that's right. It was controlled. Yes. So Ringworld is unstable. A rigid ring around a planet, you have to do something, or it develops one of these instabilities. It becomes eccentric and runs into the planet in the end. So ever since then, all planetary rings people have grown up knowing that Maxwell proved that rings couldn't be solid. They had to be individually orbiting little moonlets in their own Keplerian orbits. So Scott sort of violated that and said, well, maybe that's not true. Maybe up to a certain width they can be. And he went back and found that Maxwell had made various simplifying assumptions about the rigidity of, he was literally looking at a rigid hoop. And he said, well, okay, what if it's not really rigid, but it's locally strong, but it can deform? And you can get around Maxwell's problem. And Scott said, what if there's stickiness? We know the rings are made of ice, and we know they're densely packed. Maybe the ice sticks together. And people had done some numerical simulations that showed if you put stickiness in, it could easily happen. So he said, how wide a ring could you have that could stick together and withstand Keplerian shear, given sort of reasonable assumptions about stickiness? And what he found was that maybe you could make a 100-kilometer wide ring rotate with no shear. It could rotate rigidly. And it wouldn't do it forever. It would eventually fall apart. This was not a permanent structure. But at any given instant, you could have chunks of the ring that were up to 100 kilometers wide. And 100 kilometers is one tick mark on this scale. It's about the width of these features here. This one is maybe 200 kilometers. But most of these are about 100 kilometers or a bit less. So these are about the size of the structures that Scott envisioned. And he even said they might not go all the way around the planet. These might be limited ones, although these features, these are 3 different occultations, and you can see that the structure is independent of azimuth. We any occultation we get, this particular clump shows up in all of them. So these do actually go all the way around the planet. Right. So the thought is that, these are kind of like ice rafts. These are icebergs that have temporarily locked themselves together, and the shear is taken up in between, in the fluid regions in between. So you have enhanced shear in the regions in between, and then you have these locked regions. And it would seem to me that the locked regions, although Scott didn't talk about this, would probably be much more opaque, because effectively you're locking all these particles together. The shearing regions would probably be lower optical depth. So just maybe, although I can't prove it, we're seeing some alternation between these locked sort of crystalline regions in the rings and these lower optical depth shearing regions in between.
You still don't have wave structure inside them, even though being locked, or that missed out on the fires. So they still have that wave structure. Oh no, you didn't check that here, right?
No, that wave structure is in the A ring. In the B ring, there's some evidence that there is wake structure from the model, but in reality it's only in the low optical depth region where there's enough data that's really constraining the model. So I think all bets are off. In the opaque region, it's basically an absence of signal for us, so we can't really say. So yes, I think there are wakes in the low optical depth material, but that's not surprising. I think Toomre still rules here. There's still shear, there's clumping, there's clumps that get torn apart. But maybe if we could peek inside these opaque regions, we'd see something really interesting, which would be sort of a locally crystalline piece of ring. Hence my attempts to fit this with a model of sort of hexagonally close packed objects, which doesn't really work yet. But maybe in the next year or so when we get more data like this. So it's an intriguing problem, and it would be lovely to prove Maxwell wrong sort of 150 years later or something like this. But
Thanks.
Okay, thank you. Yes.
From my recollection, to put too much mass in there, the rings, well, maybe I'm not right. The rings should spread every. One suggestion to prevent them from spreading is to anchor when some of the units out.
Yes, right.
So
That would undoubtedly make the spreading problem worse if you put a lot more mass in, I think.
yeah.
Yes.
Okay, so could you maybe use that to put a limit on? the
You
amount of
could,
mass?
but already the A-ring is dangerous. I mean, the spreading time is only about 100 million years for the A-ring. So already it has to be either young or there is something wrong with the classical diffuse viscous disk spreading rates that everybody uses. The B-ring is massive enough that if you don't say there's a lot more mass hidden, you can plausibly argue that the spreading time may be 5 billion years. So you could make the B-ring primordial with a surface mass density of, say, 100 grams per square centimeter, which is what you would naively expect by just scaling the optical depth. But you're right, you probably get into more problems with spreading time. If the real density, this is something that mostly Glenn Stewart at University of Colorado has been suggested at the DPS meeting this year, that the density might be as high as 1,000 grams per cc in the B-ring with all the mass living inside these opaque zones that we can't look through. The other point he made, though, was that it's hard enough to imagine making the rings by breaking up a satellite with the mass densities we had been thinking of. Already you need to break up a satellite, say, the size of Mimas, which is about 200 kilometers in radius, and there's only half a dozen of those around Saturn. There aren't hundreds. If you up the mass density of the B-ring, you would proportionately increase the size of the satellite. So he was arguing at the DPS that this makes it more imperative to believe that whatever disrupted the rings happened during the heavy bombardment epoch early in the solar system. It was a large object, a comet or an in situ close satellite that broke up, and it's very hard to envision an object that big being broken up by a collision in the current regime with the number of Centaurs and Kuiper Belt objects buzzing around the outer solar system. So he was making an argument to go back to the notion that the rings really are ancient and there is something wrong with the viscous spreading calculations that imply young ages.
It could even just be a proton, it could be a protoplanetary ring in
Yes,
stage.
right. Left over. Yeah.
You're saying G over lambda vary in position?
Does what vary with?
G over lambda.
Oh, well, we think it does vary. I don't know why it varies. I mean, it looks to me like most of the variation in the ring is a variation in the ratio of gap to wake. You know, there's regions that are mostly gap and there's regions that are mostly wake. But what... I don't know, but it's... you might, but it's, on the other hand, there's no real theory for what governs. It's true that in the simulations, they're usually fairly uniform. I mean, if you increase the optical depth, the wakes tend to get larger and the gaps between them tend to get narrower. But there's no sort of detailed theory for this.
So do these wake properties depend at all on the mechanical properties of the solid?
Yeah, they do depend on the collisional properties. So the scope for uncertainty, there's some people at UC Santa Cruz about 10 years ago did a bunch of low temperature experiments where they knocked ice balls together inside a cryogenic system, so they get them down to the temperature of ice in Saturn's rings, because ice behaves more like a rock in Saturn's rings than it does out on the streets near its melting temperature here. So they did these very low velocity, they set up this elaborate pendulum suspension so they could simulate these millimeter per second collisions between meter-sized chunks of ice, and they measured the coefficient of restitution. So that data is what people use in all these numerical simulations, but there's lots of questions as to what happens if you put a layer of snow on the outside of the ice, or is it a pristine lump of ice? How fractured is it inside? So, yeah, I think there's a lot of scope for material properties of the ice to change things.
From what you showed us is lunch, you know that it's covered by sort of a rind.
We know it's covered by a rind of
And that's got it.
soft stuff, yeah. The infrared spectrum says that there are 10 micron sized grains on the surface. These are not monolithic, these are not giant meter-sized ice cubes by any means.
Okay, so Phil's going to be here today and tomorrow. There's going to be dinner and lunches if you want to join. So there will be plenty of time for reflection. Or you go out for reflection if you want to do that. Thank you.
Thank you.